Hey everybody, so we are going to talk about vector norms. So vector norms are the ways in which we look at the magnitude of a vector. And they're useful not just for looking at magnitudes of vectors, they're also useful for looking at the differences between vectors or the distances between them. And all of that stuff comes up in machine learning. So let's get into it. You're already used to vector norms. You already have what's called a Euclidean norm. The L2 norm is another name for it, which you are very used to using to look at the magnitude of a vector. If a vector is composed of three components, if it's a three-dimensional vector, it's got an x1, an x2, and an x3, then you're used to the Euclidean norm, which is x1 squared plus x2 squared plus x3 squared. Take the square root of the whole thing. That's also known as the Pythagorean theorem, and that is what we're used to as an idea for the magnitude of a vector. But in actuality, it's just one of many ways to measure the magnitude of a vector. And we often talk about these L norms as a set of named norms. And the reason they get the L in them is from the name of the mathematician who invented them, Henri Lebesgue. Probably my French pronunciation is not very good. Sorry about that. But so these L norms, they're a set of vector norms. And all the vector norms, they have properties that you're already used to because you are used to the idea of vectors having magnitude and the Euclidean L2 norm. So what are these properties of a vector norm? Well, a vector norm has to take a vector space X. So like if X is R3, if it's three-dimensional reals, and it has to map any vector in this vector space into a single real number. That is, it has to take this three-dimensional vector and turn it into a scalar magnitude. Okay, that's what maps to means. It takes anything in the vector space, maps it to a single scalar real number. Okay, we're used to that already for Euclidean norm. Another thing about these vectors norms is that they have to be non-negative. There is no such thing as a negative magnitude vector. A negative magnitude vector is a positive magnitude vector flipped around 180 degrees. Okay? So there's no such thing as non-negative. Everything's non-negative. There's no negative vectors. So again, just a reminder on how we read notation. For all vectors x in the vector space capital X, so for every possible vector in this vector space, the norm of that vector has to be bigger than or equal to 0. And, we have a couple of other things. Positive definiteness. If the vector itself is a 0 vector, then the norm has to be a 0 vector. Another thing is that we have to be able to pull out a constant to the outside of a vector norm. So if we have a constant, a real number, for all possible real numbers in the space of real numbers, and for all possible vectors in that vector space, we have to be able to take that constant, the norm of the constant times the vector is equal to the absolute value of the constant multiplied by the norm of the vector. So we can pull constants outside of the norm. And likewise, you're already used to the triangle inequality because that's just Pythagorean theorem, yo. So if we look at two vectors, x and y, and we add the norms of those two vectors together, that's got to be bigger than or equal to the norm of vector x plus the norm of x plus y. Let me say that properly. Right? So if you have two vectors, then right, and for any triangle, well, the hypotenuse has got to be equal to or smaller than the adding up the two sides, because that's just Pythagoras. Okay, so you're already used to all of these properties. These properties are just ways to say vector norms are really good metrics of the size of a vector. But of course, like with any metric, there's always more than one way to measure something. So let's talk about different ways to measure. We're already used to a Euclidean norm, to an L2, Lebesgue 2 norm. How does that work? Well, we take the hypotenuse, right? In Euclidean space, the distance between the origin and any point is the hypotenuse. So that's square the x1, square the x2, take the square root. And that's the shortcut, the hypotenuse, through Euclidean space. By the way, we denote norms, L2 norm, as having these double vertical bars. That's what a vector norm is. And then we say it's an L2 norm by putting that little 2 down there. Okay, so, that means the 2 norm of whatever the heck we're putting inside there. Now, shortcuts happen, okay? So almost all the time when we talk about any vector norm, if we don't name it, we probably mean the Euclidean norm just because we usually operate in Euclidean space. So I may get lazy at some point and write that without the 2, but just imagine the 2 as being there in those cases. Okay. So what is an L1 norm? Well, an L1 norm is also called the city block distance or the Manhattan distance. And the idea is, if you imagine this to be a block in the island of Manhattan, a city block, you can't take a shortcut through all the buildings straight the way you would in an open field. You've got to go all the way around the block. So a Manhattan distance is taking sum up the absolute values of all the components of the vector. So if it's a two-dimensional vector like we're dealing with here, then we just take the distance we travel on x1 plus the distance we travel on x2 to get to that point. So that's the absolute value of each component, however many dimensional things are. And we need those absolute values so we don't violate non-negativity, right? So we can't have negative values if, for instance, our point was down here instead, and we would have a negative x2 component. We don't want negative values. Okay. The thing is that this number system, L1, L2, we have other numbers. So another relatively common norm we will use, well, I shouldn't say common. It's a norm that happens. Let's put it that way. And it would be instead of L1, L2, we have L3, L4 that we just never see. But L infinity is a norm that sometimes happens. And the L infinity norm is just the maximum value of all the vector components. Okay. More generally, all the Lebesgue norms, also called LP norms, where P is just pick your exponent, they fall under this form. So take any, meant to do this. Take any vector component, raise it to the p power, add it to all the other vector components to the p power, and then take the pth root, 1 over, to the power of 1 over p, the pth root. So when these values are 1, we get the Manhattan L1 norm. When p-value is 2, we get the Euclidean norm. And when p-value is 3, we get something funky. And when p-value is infinity, well, that's when we get the maximum of all the vector components. So what does all this mean, right? Well, let's start with Euclidean because it's really easy to understand. So if these p-values are 2's, So it's x1 squared plus x2 squared. Let's imagine what happens as we take just a two-dimensional vector, because that's how we can view stuff, is in two space. And let's try to vary those two components to every possible number between 0 and 1, to go all the way across that range. Okay, so when our x1 component is 1 and our x2 component is 0, then we get the square root of 1 squared, which is 1. This is our vector norm. So this circle is the L2 norm, the one that's labeled with the number 2. And, we're going to get values of 1 when one of the components is 1. We're going to get values of 1 when the other component is 1, but the opposite one is 0, right? And then all through here, we're going to get, this is a circle because it's of the form, something squared plus something squared equals 1. This is the unit circle. And it is defined by having the Euclidean vector norm be equal to 1. Okay. What about the L1 norm, the city block distance? Well, it is in fact a block because the absolute value of the x1 and the x2 components have to add up, right? So if we have a unit norm, so that the value of this is 1, this is the shape of the L1 norm when we constrain the magnitude to be 1. Okay, and the infinity norm, right? It's just the max value. So it's going to be 1 all the way around because it's just going to be the max value of whichever component. So we're going to have the x1 component be 1 until the x2 component is bigger on this end. And you see all the things in between. Now this becomes interesting and important when, took a look. No, I did record. For a second I thought I wasn't recording. I apologize for the cursing. All right. So, right, this becomes important when we use these norms in regularization. So I'll bring us back to this image later to explain why this is important. But right now, just know that we're looking at unit-sized norming of two components. Okay, another thing about vector norms is that they're used in loss functions. And actually, ordinary least squares, well, ordinary least squares is actually an L2 norm of the error vector, of the residuals vector squared. How is that? Well, just a reminder, right? This is the residuals vector or the E vector. And our ordinary least squares loss function is that vector squared, vector transpose times itself, which works out to be the residual sum of squares. So it's E1 squared plus E2 squared plus E3 squared, ... But remember that the definition of an L2 norm is the square root of the sum of squares. So if we take the L2 norm of the residuals vector and we put a square on the end of it, that is exactly ordinary least squares. So ordinary least squares is an L2 kind of loss function. Okay. Well, that raises the question, hey, we know that there are a variety of L norms. Would it be appropriate to use L1 as a loss function to make a regression? Why do we have to use an L2 style norm? Well, we can indeed use an L1 norm for regression. And this is something that we'll talk about in class. It's going to be a form of robust regression, and we'll talk about why. So let's just run through the finding how this works real quick here. So we need this residuals vector, and for right now, I'm going to change the way the residuals vector is being written. Note this is purely for mathematical convenience, okay? So, because the residuals vector is going to get absolute valued, it doesn't matter if it's y truth minus the prediction or if it's the prediction minus the truth. But doing it this way is mathematically convenient for us. So for the L1 loss, what we're going to do is we're going to take the L1 norm of the residuals vector. And that's just going to be the absolute value of the first point residual plus the absolute value of the second point's residual plus the absolute value of the third one. So absolute values. Okay, if we're going to take the derivative of this to try to find the best possible set of weights, we're going to have to know what is the derivative of an absolute value. Well, the derivative of any variable a with respect to itself is just going to be 1, right? The derivative of a with respect to itself is going to be 1. So what's the derivative of the absolute value of a with respect to a? Well, it's the sine function of a. That is, when a is a positive value, just like with the derivative of a, the derivative is 1. When a is a negative value, however, the derivative is negative 1. So the sine function is just minus 1 or plus 1, depending upon what the value of a is, if it's a positive value or a negative value. Note the discontinuity there. Okay. So that means that if we're going to get the derivative of this L1 loss function in order to optimize, well, we can use the chain rule. We can take the partial of the L1 norm of the E vector with respect to the E vector, and then multiply that by the partial of the E vector with respect to the W vector to get all the way down to what we want. Well, we just saw up here that this has just got to be the sine of the residuals vector. And we know from this that the partial of that with respect to W is just the x term. So what we get is a situation where the slope of our loss function's derivative of its gradient is just going to be determined by this x. That's a constant with respect to the error. Okay, so it's just going to be some constant sloped thing where the slope is determined by x, but it's going to be positive sloped when the E vector for those components which are positive, and it's going to be negative sloped, that same slope, when the E vector is negative. So this is something which is convex, but not strictly convex. And it is also not a smooth function. The derivative is undefined right here at this point. And because the derivative is undefined right there at that point where we actually want to take the minimum, there is no analytic solution to an L1 regression. You can't just set the derivative equal to 0 because the derivative here ain't 0. The derivative here is undefined. Okay? So this kind of L1 regression loss no longer has an analytic solution. What we have to do is we have to gradient descent it. So, we'll start our weights somewhere over here, and we'll just follow downhill until we hit a minima. Okay, that's all I got for you. Talk to you in class. Bye.